Good evening, this is Keith Capellaro from K-Dawg Weather. Tonight, we're going to be talking about atmospheric rivers, understanding their roles in weather and climate. Tonight's agenda overview is definition and characteristics of atmospheric rivers, formation and dynamics of atmospheric rivers, impacts of atmospheric rivers, detection, forecasting, and climate connections. Definition and characteristics of atmospheric rivers. What is an atmospheric river? The definition of an atmospheric rivers is atmospheric rivers are narrow corridors carrying concentrated moisture from tropical to mid-latitude regions in the atmosphere. The scale and size. These rivers can be thousands of kilometers long and hundreds wide, transporting huge volumes of water vapor. Role in precipitation. Atmospheric rivers deliver significant precipitation, especially to western coastal areas of continents worldwide. Key feature and scales. Dimensions of atmospheric rivers. Atmospheric rivers are elongated, typically 2 to 300 kilometers wide, and extend over 2,000 kilometers in length, showcasing their massive scale. Occurrences and wind speeds. They commonly occur in mid-latitude storm tracts with wind speeds often ranges from 30 to 50 kilometers an hour or higher. Impact on weather and precipitation. Atmospheric rivers influence weather over large areas and can deliver up to 50% of annual rainfall in some regions and lasting for days. Comparison with other weather phenomena. Distant structure of atmospheric rivers. Atmospheric rivers are linear moisture bands tracking the cyclonic rotation seen in hurricanes and storms. Difference from frontal systems. ARs act mainly as moisture transport conduits, unlike frontal systems that separate warm and cold air masses. Precipitation compared to storms. Atmospheric rivers can deliver precipitation amounts comparable or greater than monsoons and tropical storms. Formation and dynamics of atmospheric rivers. Meteorological conditions leading to formations. Moist air advection. Moist tropical air moves poleward, driven by prevailing winds and low-level jets forming atmospheric rivers. Key meteorological factors. Strong pressure gradient, sea surface temperature, contrast, and active storm tracks contribute to atmospheric river formations. Frontal boundaries, ongoing lifts, and cyclonic systems promote condensation and precipitation intensification with atmospheric rivers. Flow of atmospheric rivers. Atmospheric rivers channel warm, low-level jets that transport water vapor efficiently across long distances. Vertical moisture temperature transport factors. Vertical moisture fluxes, wind speeds, and humidity gradients govern the efficiency of moisture transportation in atmospheric rivers. Precipitable water amount. Atmospheric rivers can carry 2 to 5 centimeters of precipitable water, focusing moisture and delivery within limits spatial extensions. Conveyor belt analogy. Moisture transport acts like a conveyor belt, linking ocean evaporation to continental precipitation with minimal losses. Interaction with landforms and oceans. Orographic uplift effects. Atmospheric rivers cause increased precipitation when lifted by coastal mountains, leading to heavy rainfall or snow accumulation. Moisture lasts over oceans. Atmospheric rivers lose moisture due to evaporation and condensation over warm ocean surfaces, affecting moisture availability. Impacts on weather patterns. Interaction between atmospheric rivers and oceanic circulation influences storm tracks and regional water resources. Impacts of atmospheric rivers. Effects on precipitation and flooding. Atmospheric rivers and precipitation. Atmospheric rivers contribute 30 to 50% of annual precipitation on the U.S. West Coast and parts of Europe. They transport large moisture volumes, causing intense rainfall, flooding, and extreme weather. Heavy rains from atmospheric rivers lead to flash floods, landslides, and ravine flooding, impacting communities severely in short time spans. Case study: 2017 California event. The 2017 California atmospheric river event caused record-breaking precipitation and flooding with damages exceeding $1 billion. Influence on drought relief. Atmospheric rivers and precipitation. Atmospheric rivers deliver concentrated precipitation that replenishes reservoirs, groundwaters, and snowpack in drought regions. Drought alleviation potential. A few atmospheric river events can alleviate multi-year droughts and improve water supply reliability significantly. Vulnerability challenges. Variability in frequency and intensity of atmospheric rivers complicates forecasting, predicting drought relief benefits. Economic and environmental consequences. Economic damages and costs. Flooding from atmospheric rivers costs billions in infrastructure repairs and disruption business activities, impacting economies. Environmental impacts. Heavy precipitation leads to erosion, habitat disruption, and reduced water quality in affected ecosystems. Ecosystem benefits. Atmospheric rivers also support freshwater availability and forest health, enhancing ecosystem services. Detecting, forecasting, and climate connections. Modern methods of monitoring. Satellite imaging and profiling. Advanced satellites deliver high-resolution imagery and moisture data essential for accurate AR detection. Ground-based sensor, radar, radio nodes, and remote sensors verify moisture and wind pattern to support satellite data. Integrated monitoring networks. Combining satellite and ground data enables near real-time AR tracking and enhanced early warning systems. Forecasting challenges and advancements. Forecasting challenges. Accurately modeling moisture transport, storm dynamics, and terrain interaction remains a key forecasting challenges. Numerical weather prediction advancements. Advance in numerical weather prediction and data assimilation provides forecast lead times and precision. Machine learning and ensemble forecasting. Machine learning and ensemble forecasting helps quantity uncertainty and enhance flood risk predictions. Role in climate change and vulnerability. Increase moisture captivity. Climate change raises atmospheric moisture capacity, intensifying precipitation and frequency of atmospheric rivers. Extreme weather events. Heightened atmospheric river extremes may cause more frequent severe floods and drought variability worldwide. Adaptation strategy importance. Understanding atmospheric river changes is critical for developing effective climate adaptation strategies in vulnerable regions. Okay, the conclusion. Atmospheric rivers are key drivers of weather and climate dynamics. Role in weather patterns. Atmospheric rivers critically influence weather patterns by transporting large moisture quantities across the region. Impacts on climate variabilities. These phenomena affect climate variability and play a part in seasonal and long-term climate shifts. Importance of monitoring. Advanced monitoring technique improves forecasting and disaster preparedness for atmospheric river impacts. And I want to thank everybody. This is Keith Capellaro from K-Dawg Weather. I want to thank you very much. And please like and subscribe to this channel. Thank you, and have a good day.